In this talk, I'll present you my recent work, training resilience with persistent memory coding using CXL technology. This work is done by me and my great colleagues, and is a joint work with Connection. Before moving on to the main talk, let me briefly summarize the talk. This work is about efficient training of recommendation models, or RMs for sure, which is a dominant workload in production work center nowadays. However, it is a challenging workload since it requires a failure-tolerant system with a large memory. In this requirement, recent works try to employ SSDs to expand the available memory spaces. However, their performance is limited due to the long latency of SSDs. To address this problem, we propose TrainingCXL. TrainingCXL employs a persistent memory disaggregated over a CXL network, which provides large memory space with high performance. Also, it leverages PMEM's persistency with automatic low checkpointing to make the system failure tolerant. Our evaluation showed that TrainingCXL exhibits 5.3 times shorter training time compared to modern PMEM-based systems. I'll start the talk by introducing the target resource domain and its As introduced earlier, this work is about efficient training of deep learning based RMs. The deep learning based RMs are one of the most successful applications of machine learning and is widely used in diverse product services of companies like Meta, YouTube, Amazon, and Netflix. Due to their wide adoption, recommendation model training became a dominant workload in data centers. For example, Meta recently stated that more than half of Meta's power resources for deep learning training are used for recommendation models. Before discussing the challenges of RM training, I'll briefly introduce how RM training works. For an accurate recommendation, RMs use both sparse features and dense features. And the user gives multiple pairs of sparse and dense features called a batch. RMs encode the features into a vector and then pass it through a main model for top multi-layer perceptron of top MLP in short, to generate the final output such as the fluent. Encode sparse features to vectors. RMs employ an operation called embedding lookup. It uses the indices in the sparse features to look up their corresponding vectors from an embedding table, and then reduce their vectors to one or more vectors. On the other hand, dense features are processed by another MLP, which performs a nonlinear transformation using matrix multiplications and nonlinear functions. Considering the computation intensity of operations, the embedding lookup is processed in CPU, while top and bottom MLPs are processed in GPU. These processes generating output are called forward propagation. After forward propagation, RM training performs backward propagation, which adjusts the model parameters so that they can generate more accurate output next time. In particular, the backward propagation visits the operations in forward propagation, again, with the reverse order to calculate gradients. The gradients are then used to update the model parameters, and this forward and backward propagation is repeated for other batches until the training is done. The critical challenge in recommendation model training is its large memory consumption. Similar to other deep learning models, the RMs gets more accurate when we increase model size by having larger embedding tables. For example, Baidu has shown in their research that their model gets 3% higher accuracy when they increase the model size by 10 times. Note that this 3% is a significant amount in terms of accuracy gain, which is enough to increase the revenue of the service. Plus, hyperscalers have rapidly scaled up their recommendation models. For example, Meta increased their model size by 10 times in only 3 years. As a result, the recommendation model is now considered the largest deep learning model, achieving terabytes of memory. It's even much bigger than transformer-based models, such as ChatGPT, which is gone quite viral these days. To address this challenge, recent works propose SSD-based memory expansion approaches for recommendation model training. They store the large embedding tables in SSDs while leaving host DRAM as cache. However, we found that SSD-based approaches have multiple challenges and limitations. The first one is they exhibit low embedding lookup performance. While SSDs are optimized for both sequential accesses using multiple flash chips in parallel, the embedding lookup operation mainly consists of small random reads. Thus, SSD-based embedding lookup shows low performance, which makes SSD unsuitable for storing the embedding tables. Further, their system shows a non-trivial data movement overhead. After performing the embedding lookup, the reduced embedding vector must be transferred to GPU to pass them through top memory. However, since data transfer is done by software, the host should wait until all the reduced embedding vectors are ready, leaving PCI interconnect. After this synchronization, the system transfers the data to the GPU and then continues processing the NLP. This data movement procedure directly puts its latency on the critical path, thereby degrading the overall. The last part is that the system exhibits non-trivial overhead for checkpoint. While training requires days or weeks to be done, the typical period of machine or job failure is only several hours. Thus, RM training is likely to face multiple failures during training, which makes the system failure tolerance important. Since SSD is a persistent storage, one might think of persisting the update by directly updating the vectors into underlying SSD. However, SSD's write performance is orders of magnitude slower than local memory. This approach suffers a serious performance degradation, which makes it unpractical. Therefore, all of the existing approaches use checkpointing approach to make their system failure tolerant. They first update the embedding vectors to the host DRAM, then it periodically saves the snapshot of the latest embedding vectors to SSD as a checkpoint. While this approach reduces the amount of write, thereby exhibiting better performance, the checkpointing still accounts 12% of the training time, which is not true. To this end, we propose TrainingCXL, which addresses all the issues of recommendation model training. I'll first give the overview of our system and then discuss the detailed design. TrainingCXL is a system that enables sufficient large-scale failure-tolerant RM training with minimal data movement overhead. TrainingCXL consists of three design components. The first one is the persistent memory disaggregation that provides large memory space. It employs multiple memory expander devices attached with persistent memory called CXL-MEM. They are connected to GPU through the CXL switch. This CXL network can provide up to 4 petabytes of memory space, which can easily suffice the memory demand of RM training. Second, by designing the devices as CXL Type 2 devices, we enable CXL-based automatic data movement, which can remove overheads coming from the software intervention. Lastly, we leverage the PMEM's persistency to make the system failure tolerant while reducing the accompanied overhead by being aware of RM training's characteristics. The CXL-MEM device is composed of a front-end and back-end modules. The back-end employs multiple PMEM modules and corresponding memory controllers to achieve a high degree of data parallelism for large-scale embedding cables as well as model checkpoints. The aggregated memory space of PMEMs is exposed to the front end through the system interconnect. The front end consists of a CXL controller that implements the CXL protocol, a computing logic for processing embedding operations, and checkpointing logic that automatically creates the model checkpoints. The CXL network exposes CXL GPU and MEMS internal memory to a unified physical address base called a host physical address. To automate the data movement and remove the software intervention overheads, we designed the CXL CPU and MEM as a CXL Type 2 devices. To implement the type 2 devices, we introduce device coherency engine to devices. This engine tracks the state of the internal cache lines and enables CXL cache protocol to query. The CXL cache protocol allows the device to access the data residing in other devices via load store like instructions in a cache coherent way. Since CXL cache manages the cache coherence for each cache line, we can overlap the computation time and data movement time with granularity of cache line. For example, when CXL GPU should send the gradients to CXL-MEM, device coherency engine flushes the corresponding cache line to CXL-MEM's memory as soon as data is ready. The CXL-MEM can then read the data from its memory and then perform the embedding update in a cache line granular pipeline. Now I will explain the detailed design of TrainingCXL. First one is the failure tolerance management. Typical applications such as database systems cannot know the exact location of data updates before the computations. Therefore, their failure tolerance management, such as checkpointing or a write-ahead log, are performed on demand, exposing their overhead on the critical path. However, for RM training, the update locations are available even before the computation. This is because the backward propagation updates the vectors that are involved in forward propagation, which is available as indices in sparse features. Thus, TrainingCXL leverages this characteristic to take the checkpointing overhead off the critical path by performing checkpointing in advance in an undo log manner. Specifically, we split the CXL-MEM's memory space into data and log regions. The data region is for computer logic to store embedding tables, and the log region is for checkpointing logic to store embedding logs. When the sparse features are given, the computing logic processes the embedding lookup and sends the reduced embedding vectors to CXL GPU. Next, while CXL GPU is processing the top MLP, CXL-MEM performs the checkpointing in advance. Specifically, it copies the vector corresponding to the sparse features from the data region to the log region after all after all the copies are done. The checkpointing logic completes the log by writing a persistence flag, which means that the log is valid. If there is a power failure, the CXL-MEM can recover the RM model by loading the latest checkpoint with a persistence. The end TrainingCXL can update the embedding table without suffering from a checkpoint. The second detail is the relaxation of training, which detours the PMEM's performance vulnerability. Normally, the PMEM exhibits DRAM-like read performance. However, if the read request comes to pure media right after write, the performance can be significantly degraded. This is because the read request must wait until the write in PRAM media cools down its thermal core. Fortunately, this can frequently happen between the embedding update and the lookup between the consecutive batches. Due to the inherent locality in RM, frequently accessed vectors exist. As shown in the center of the slide, they are highly likely to be updated and then read by the following embedding lookup operations. This read after write can degrade the overall embedding lookup. To solve this problem, we focus on the commutative property of embedding lookup and update. Since the update and lookup are subtraction and addition-based vector arithmetic, the final result stays the same even if we change the execution order. Thus, we relax the dependency between consecutive batches to avoid read after write. Specifically, we split the embedding lookup of the following batches into two steps. The first step performs the embedding lookup prior to using the embedding table of a preceding batch. The reduced vector of the first step is stored in the internal SRAM buffer rather than PNAND. Then the second step updates the reduced vector in the SRAM buffer by subtracting the gradient multiplied by the learning rate. As a result, TrainingCXL can make the result identical to the original execution while enjoying the DRAM-like read performance. Last, I'll briefly show our evaluation results, then conclude the talk. We evaluate the overall performance by measuring the execution time for a single batch. By saving the embedding table on disaggregated persistent memory instead of SSDs, the system improved the execution time by orders of magnitude. By accelerating embedding lookup and update in CXL-MEM, the system showed 2.8 times shorter execution time. Finally, our TrainingCXL overlaps the computation and data movement time, as well as employing RM-aware checkpointing, thereby improving the performance by 1.9 times. As a result, TrainingCXL achieved 5.3 times faster performance than the baseline PMM-based system total. In conclusion, we propose TrainingCXL, an efficient large-scale failure tolerance system for RM training. TrainingCXL enjoys the large memory space by disaggregating the persistent memory over CXL and overlaps the data movement to a computation via CXL-based cache line granular automatic data movement. And it also makes the system failure tolerant with low overhead by being aware of RM's. Thank you for listening, and I'll be happy to